Okay. So let's look at the group S3. I think we were doing. So it's the first smallest group that is not a billion, 46. And we'll describe all the irreducible representations by hand, and then later some of the things we'll find we'll do in general. So our group is S3, S6, and it's generated by two cycles that are called sigma and tau. So tau choose the free cycle 1, 2, 3, and sigma the cycle 1, 2. So there's two representations that we should be able to spot right away. And which are these?
By conjugation, that we take the action by conjugation.
On where?
Sorry?
Acting where?
G acts on itself by conjugation.
Yeah, maybe that's not the simplest. I'm thinking something much simpler to begin with. Yeah, that's what we're going to do in a second, but even before that, there's something much simpler.
R3 and consider this as permutation on the...
Yeah, that's what Carlos is saying. Even easier.
Trivial representation.
The trivial representation. Every group has a trivial representation. Yeah? And although it's trivial, you should not discard it. I mean, right? 0 is a very important number. But there's another one. Less trivial, but also fairly easy.
You said, I think I said?
I said my multiplication.
No, even easier. Dimension 1, degree 1.
Constant.
Huh?
It sends all the elements to identity. I'm sorry, just the
Is what we'll call the sign representation. You take a permutation row in general in the symmetric group of n elements, and you can attach to it the sign, which is plus if row is even, minus if row is odd. You must have seen this in algebra. This is a homomorphism, right? The sign of a product of permutations is the product of signs. So this is a homomorphism. So indeed, this is a one-dimensional representation. And these two, the trivial and the sign, exist for every n, right? And in fact, the group Sn for n at least bigger than 5, bigger or equal to 5, we'll do by hand the groups S3 and S4, has only one normal subgroup, which is An, and Sn divided by An is of order 2, so it has to be the cyclic group of order 2. We'll write C2, cyclic group of order 2. And An is the commutator subgroup of Sn. So, as we said on Monday, every representation, every map from S in general from a group to C star homomorphism has to factor through the commutator subgroup. In this case, factors through AN. So the only homomorphisms from Sn to C star are this, the trivial map and the sign. Yeah. So Sn in general, well, as I said, at least from 5 on, has only 2 one-dimensional representations, which are the sign and the trivial. Okay, so these are always there, and they're the only ones of dimension degree 1. So now we can move on and try to find other representations, or understand other types of representations. And yes, we could do what Carlos and Foxy was saying. We could just have S3 act on the set 1, 2, 3, just the tautological, or just the defining representation. The S3 is, by its very nature, acting on 3 things. Okay, so this is a permutation representation. It just permutes the elements of the set, so we call it set X. And associated to any permutation representation, we have a linear representation, which is on a vector space of dimension equal to the size of the set. So in this case, this is 3. So it acts on the 3-dimensional space by permuting the coordinates. But recall that I wanted to stay with left actions. So let's record what tau does. We did this calculation on Monday, but if our vector has coordinates A1, A2, A3, then let's take T of A1, A2, A3. Let's do one at a time. So A1, A2, A3 is taken by tau to what? This we did last time. A3, A1, A2. Somehow you have to follow your symbols, and it's not exactly what you may first think. If you want to stay, as I said, with left actions, and then sigma, in this case, because it's only 2 things, whichever way you do it, it will come out to be the right one. And it permutes A1 with A2. Okay? So this is the way this representation works. It acts, it's a 3-dimensional representation. A group acts, you can think of R3 if you want to think geometrically, but our base field is C, so it's not something we can easily draw. But so I'm going to call it linear representation rho. So just to fix ideas, if we have chosen a basis in a vector space, so rho of tau and rho of sigma are matrices. Let's figure out what those matrices are. Well, here we have what it does in terms of coordinates. So what's the matrix for tau?
0, 0, 1, the first row.
0, 0, 1.
I like to. Is it easier to think of columns? What's the first column?
The first column.
First column is where the first vector goes, right? So the vector 1, 0, 0 goes to
0,
0, 1, 0. the vector 0, 1, 0 goes to
0,
0, 0, 1. And 0, 0, 1 goes to 1, 0, 0. And rho sigma 0, 1, 0, 1, 0, 0, 0, 0, 1. Yep. So now we have a concrete description. These are matrices, invertible matrices in GL3. I mean, there's 6 matrices, right? The group has, or 6, but I'm focusing on the generators because if we know what the things happen with the generators, then we can deduce what will happen with the others. So I just want to point this out because what kind of matrices are these? Yeah, but they have a special name. They have a
SL2?
Huh?
They are part of SL2, I think.
Doesn't look like it. I mean, they're in,
SL3.
they're in GL3. No, they're not gonna in fact have determinant 1.
Oh.
This one doesn't have determinant 1.
Permutation matrices?
Yeah, so these are called permutation matrices. As they, how are they characterized?
One each column row.
They have only a 1 on each row and column, and everything else is 0. Okay, so you can extrapolate from here that in general we'll have a representation of Sn into GLN where a matrix, a permutation tau will go to the permutation matrix corresponding to tau, which will be the analog of this, and this will be a matrix that has a only 1, 0, only 1, 1 in each column and in each row. Okay. So the now we haven't formally defined this, but let's do this example and define it later. So this is a vector dimension 3 where the group acts, and we will be interested in things that are irreducible. And irreducible means that there is no sub-representation that is not either the full space or the zero space. So a sub-representation is a subspace on which the group also acts. Yeah. So here, this is a space of dimension 3. So I claim that there is a line, a vector space of dimension 1, which is a sub-representation. So a line that is actually completely fixed by the full group, by the entire group. And what line is that?
The line generated by the vector 1, 1, 1?
Right, so the vector 1, 1, 1 and the line that it generates, so the subspace U generated by this vector U is completely fixed by the whole group, because the group permutes the coordinates, and certainly if all the coordinates are the same, then you don't see the difference. So this is a sub-representation, and it's not 0 or the full space. So this representation that we talked about, I'll come back to this more formally, but it's not irreducible. And So it's a non-trivial, a sort of proper sub-representation. So hence, V is not irreducible. Now, what we're going to see, and so as I said, I'm going to go over this example slowly and by hand, and much of what we're going to do, we'll do it more theoretically in general later. So, our vector space contains this subspace, this line, and if you have a vector space and a subspace, then you can always find a complementary subspace. But what we are interested in is in the world of representations. So, well, what we like to say or decide is if there's a complement to this vector space U that is also a representation. I mean, if I give you a subspace U of a vector space V, then many different complements, right? I mean, in any plane that doesn't contain the line will be a complement. But the question is whether we can find a complement that is actually itself a representation.
Yes, because if the two of the three are not the same and we make a permutation, they are still not the same thing.
Yeah, but then they might be, they will come out of this subspace. We're looking for a subspace W. So what, this is of dimension 2, right? So we're looking for a plane in this three-dimensional space that itself also stays stable under the action of the group. If you permit, sadly, if you take any vector that is not in the line, it will be moved.
Still not on the line.
Sorry?
It will not.
It will not come into the line, but it may come out of the subspace W that you chose. Yeah, we have to pick this W carefully. If you just want to find a complement of a vector space, there are many ways of doing it. But we're looking at a very particular subspace, if we can, for which the subspace itself is invariant under the action of the group. So W itself, so what we want is W, which is a complement in the sense that this holds, but is itself a representation. And what we'll see later is that any sub-representation of a representation has a complement which is also a representation. Okay, which is not completely immediate. And in fact, it will use, for example, strongly that we have a finite group and that our field is a characteristic 0. This will fail in general otherwise. Okay, but here, let's just do it in this case. What should we take to be W? There's not a lot of choices, in fact. But how do we describe W?
The orthogonal plane to the right?
Yes, but orthogonal with respect to what?
The plane passing through the origin with this vector orthogonal to it.
Yes. Okay. I think I'll come back to that, but I think we can give this in a much simpler way. I think it's equivalent to what you're saying, but it's simpler to describe. Give me an equation for W. So a subspace you can either give by giving a basis of the subspace, or you can give it as equations for it. And in this case, it's easier to give the equations for it.
A plus B plus C equals 0.
So indeed, if we take, well, we're using A1 to A3, so I can take W to be the triple in a vector space such that the sum is 0. Because the group permutes the coordinates, the sum stays the same. So if the sum was 0 to start with, it will be 0 after you apply a permutation. You apply the representation. And this is certainly a dimension 2 vector space, and is complementary to the line. And is orthogonal, as I said, with respect to the usual Hermitian product on the space. And in fact, as we'll see, this is one way to prove that there's always a complement, is to find an appropriate inner product and then take the orthogonal. Okay, so here's a W. Now this is a dimension 2, this is dimension 1, this is dimension 2, and this is dimension 3. And so I claim make one observation first. That this V came from a permutation representation. So any V coming from a permutation representation, as the one we are looking at, contains a one-dimensional subrepresentation, like our U. And to see this, we define our vector space as the space of functions from the set X. So here the situation is G is acting on the set X, and our space was defined as the space of functions where G acted on a function F on an element X is F of G inverse X. So this describes an action of the group on the functions, which is a vector space. So this is a linear representation. So what's the one-dimensional subspace that we can say is always there? That is always a subrepresentation.
Changing every X to 1?
Or sending every X to anything. Okay, so the functions that are constant, these will always be this action preserves the function. If a function is constant, after you apply the group elements, it still remains constant. Yeah, because the value of the new function at X is the old function at some other point on the set, but if the function is constant, then these values doesn't change. So we always have a subrepresentation which is of dimension 1. So if the space V is dimension bigger than 1, this will mean that we have an actual proper subrepresentation. So V is never irreducible. Okay, so the corollary of this observation is that V, if V is dimension bigger than 1, then V is not irreducible. I'm talking about V coming from a permutation representation, no, not just arbitrary. Okay, but so we can always peel out a line a one-dimensional space that is a subrepresentation, and we're left with something. In the case that we're dealing with, this dimension 2 representation, but what I want to show now, so in our case, the complement W is irreducible. And irreducible means, by definition, that it doesn't have representations, sub-representation, proper sub-representation. So W is a dimension 2, and to say that it's irreducible, to say it has no proper sub-representations, is to say there's no line that is fixed by the group. Okay, but let's analyze this W a little more than just proving it's irreducible. So, so consider the way that tau, the action of tau on W. Tau is an element of order 3. Tau, remember, is the cycle 1, 2, 3. And if we just consider what tau by itself does, tau generates an abelian group of order 3, cyclic group of order 3, and is acting on this two-dimensional space. And so tau, recall what we said earlier, rho of tau is diagonalizable. With eigenvalues which theta with theta cubed equal to 1. So W will break up into two lines by the action of tau that are eigenvectors for tau. So can you tell me two eigenvectors of tau on W?
We have already one, the vector 1, 1, 1.
No, that's not in W. We took it out. We're looking at the complement. So that one we already know. So we're looking at the remaining things.
1 minus 0 minus
No, I don't think that will be. So tau just cyclically permutes the coordinates, right? So let's see, maybe we can just do it. So tau, recall A1, A2, A3, or rather rho of tau, A1, A2, A3, it's A3, A1, A2, we said, right? And so what we want is this to be theta of A1, A2, A3 for some scalar theta. We know that scalar has to have a cube that is 1. So then what we're saying is that A3 has to be theta A1, A1 has to be theta A2, and A2 has to be theta A3. So if we solve these equations, what we see is that, let's see, A2 is zeta A3, which is zeta square A1. And so we get the vector A1, A2, A3 is A1 times 1, zeta 2 is zeta squared, zeta. Right? So if zeta is equal to 1, then this is the vector 1, 1, 1. I mean, we're looking for an eigenvector, so we in fact can ignore A1. If A1 is 0, then it's the 0 vector, which is no good. So zeta equals to 1 just gives rise to the vector 1, 1, 1, which is not in a space W. But if zeta is equal to say e to the 2 pi I over 3, which is the other possible, one of the other possible cubic roots of unity, then this actually gives us a eigenvector with this eigenvalue. So what I can do then is take, let's call this call this thing zeta 3. Then I have two vectors. I can take this vector and this one. By choosing zeta to be either zeta 3 or zeta 3 inverse, zeta 3 squared. And these two are eigenvectors, so tau of W1 is zeta 3 squared W1, and tau of W2 is zeta 3 of W2. So if we just have tau by itself, the space W is a sum of two lines. They two generate the whole space W. So W is C times W1, direct sum C W2. Yeah, these two vectors are in fact independent. They span the space. And tau acts on them by a diagonal matrix because it's they're both eigenvectors. So we basically found a basis on which tau is diagonal. Now, a group doesn't consist just in tau, but also has sigma. So let's see what does sigma do. So, what is sigma of W1? We permute the first two coordinates. So this is zeta 3, 1, zeta 3 squared. Okay, and this is in the space W. W is a representation for the whole group. And so how do we write this in terms of W1 and W2? Well, this is zeta 3 times 1, zeta 3 squared, zeta 3, yeah? And this is zeta 3 W2. And sigma of W2 is zeta 3 squared, 1 zeta 3. So this is zeta 3 squared, 1 zeta 3 squared. So this is zeta 3 squared W1. So that means that in this basis, and recall that we're interested in representations up to isomorphism, so change in basis gives us a isomorphic representation. So mapped to GL3, which is conjugate to the one we had. So in this basis, given by W1 and W2, G acts by the following. So tau is what matrix? It's a 2 by 2 matrix. It's what matrix? So tau on this basis acts diagonally, right? So in W1 it acted by zeta 3 squared, and on W2 acted by zeta 3. And sigma, we have it right here, W1 goes to zeta 3 W2, so not quite diagonal, but sort of anti-diagonal. And W2 goes to zeta 3 squared W1. So I claim that this shows that this W is irreducible because there is no line that is fixed by the whole group. Because if a line is fixed by the whole group, it has to be fixed by tau. And there's only two lines that are fixed, not as a set, but not pointwise, but as a set, which are the two lines spanned by W1 and W2. Because anything that is fixed by any line fixed by tau has to correspond to some eigenvector, some eigenvalue. So the only two possible lines fixed by tau are the W1 and W2, and sigma just swaps them. Yeah? So there is no, this implies there's no line fixed by both tau and sigma. Hence, W is irreducible. So this W is then one of the guys that we will be interested in doing for any group, which is to describe the irreducible representations. And W is called the standard representation of S3. And the same thing that we did for S3, you can do for Sn. So in general,
sorry, why is no line fixed by both tau and sigma?
because you have the only possible lines fixed by a whole group are lines that are fixed by both sigma and tau. And tau only fixes two lines. It's eigenvectors, it's eigenlines. And sigma does not fix them because it swaps them. And therefore, there is no line that is fixed by both. So this is to say what I think I mentioned on Monday. Each individual element of the group can be diagonalized. But this is a clear example that you cannot necessarily diagonalize all elements of your group at the same time, on the same basis. So if you diagonalize tau, you have to do it in this basis. There is no other option, or up to scaling. And if you do that, then sigma isn't diagonal. We could have done also the other way around, and we could have found the basis where sigma is diagonal, and then find what tau does there, and we'll just find out that it's not diagonal there. So this is where the non-commutativity of the group G plays a role. In the commutative case, we'll come back to that, but in the commutative case, all representations are sums of lines, and so there is in fact a basis on which all matrices are commutative. Okay. But in the non-commutative case, this is not the case. Okay, so in general, Sn acts by its very definition on n things. We get a corresponding representation V at dimension n, which is a linear representation, just as we did. As because it comes from a permutation representation, again the vector of all entries equal to 1 is fixed. The vector's subspace where the sum of the coordinates equal to 0 is also fixed. So this is dimension n, this is dimension 1, and this is dimension n minus 1. And we'll probably, I think we might get to this, but let me just say it, announce it now. W is irreducible. So it gets n bigger than 1 for every n. So we did it by hand for n equals to 3, but it's in fact true for any n, and this is called the standard representation.
But in the case of 2, it is still...
Yeah. It's just a line. Any one-dimensional representation is irreducible. Yeah, so the difficulty here is that this type of fairly simple-minded argument that we use becomes much more cumbersome and probably not doable for if you try to do this for all n at the same time. But so once we develop the theory is incredibly powerful, and something like this becomes very sort of tractable, and there's a very pretty proof that this is the case, and you do that for every n simultaneously. Okay, so in fact, so what do we have? We have 3 representations that we found. We have the trivial, we have sine, and we have the standard for S3. And I claim these are all the irreducible representations that there are. And again, I'm doing this as a warm-up just to get acquainted with the various issues, but we'll come back and prove statements like this for any finite group. So what I'm claiming now is that these here are up to isomorphism all irreducible representations of S3.
Excuse me, but since any group is isomorphic to a subgroup of Sn for some n, have we classifying the representation of Sn gives us a classification for all the representation of finite groups, right?
Unfortunately not. It does give you something, but not enough to. It's, I think, in fact, not a particularly useful statement. There's, given a finite group, there's many different ways that you can view it as a permutation group. The standard proof that it's a subgroup of Sn is by acting on itself, and that gives you an enormous Sn. So N is the size of the group G. That's just way, way big. It's just not good. So in fact, that's not how one proceeds to understand the representations of a finite group typically. Depending on the case, maybe those ideas would be helpful. But for example, the group you may know has a map to a relatively small Sn, and then that you can use. But it's hard to say something very general. So let's try to prove this claim. So let's say V is a representation of our group G. G is S3. And basically we're going to do what we did for our special case of W. And in fact, this is something that one does in a bigger context. It's called the Unitary Trick. But regardless, we first consider what tau does, and then decompose it according to tau, and then see what sigma does to the pieces. So tau, as we said, is diagonalizable. Because, as we argued on Monday, it's a finite order. Well, I'm abusing notation. Rho of tau, right? So tau, I'm viewing it as a linear map from V to V. So if tau of a vector V is lambda V, or maybe I'll just use theta. We know already that theta cube has to be 1. Then what happens with sigma? Well, tau and sigma do not commute, but tau sigma is tau inverse sigma. The group is in fact isomorphic to the dihedral group. Write this correctly. Tau sigma, right? Tau sigma is sigma inverse. This is the dihedral relation. The group S3 is actually isomorphic to the dihedral group of order 6. I never remember, do we write this D3 or D6? It's a group of order 6. So if I take the vector that is an eigenvector for tau and apply sigma to it, what happens? Well, let's see what tau does to the result. Tau sigma of V, this is by the way representations work. Representations are homomorphism, so if you apply first sigma then tau, that's the same as applying the product. And tau sigma is the same as sigma tau inverse. And so this is the same as applying tau inverse to V and then sigma. But if tau acts on V as say that V, then that means that tau inverse of V has eigenvalues theta inverse. Theta is a scalar, commutes with everything, so this is the same as theta inverse sigma V. So if V is a eigenvector with eigenvalue zeta for tau, then sigma of V is an eigenvector with eigenvalue zeta inverse. So V is a direct sum of three eigenspaces. These are V zeta is defined to be the zeta eigenspace for tau, which could be 0, but it's the tau is diagonalizable, so it breaks up the space into its eigenspaces. So there is sum. And if we look at the first, so we look at what sigma does to these pieces. So sigma of, so I'm going to, circle. So if zeta in that argument is 1, which is one option, then zeta inverse is also 1. So that means that sigma V belongs, is also fixed by tau. So what I'm trying to say here is that V1 is sub-representation. Because being in V1 means that tau fixes the vector. And by this argument, if tau fixes the vector, then sigma V also is fixed by tau. Yeah. So, right? I mean, this argument here. This was an assumption. The assumption here was that tau V was zeta V. So if I look at the case where zeta is equal to 1, I get that sigma V is also fixed by V, by tau. Is that clear what I'm saying? So if you look at that, I'm saying tau of V is V, and I claim that sigma of V also is sigma V.
Yes, that's clear, but this doesn't mean it is a sub-representation.
That's exactly what it means. Every vector in V1 is taken to V1 both by tau and by sigma. And since tau and sigma generate the group, any element of the group will do that. Yeah. So if I start with a vector that is fixed by tau, then by definition tau takes me to the, well, in fact it completely fixes it, but if particular it stays inside the space. And this argument here says that sigma V also stays in the same subspace. Yeah. Now what happens? Okay, so okay, let's look at this case. So now we have a sub-representation of V, where tau acts trivially. Yeah. But how about sigma? Sigma is an element of order 2. So, and it acts in V1. And so by the same argument, it breaks up as eigenspaces for sigma. Sigma is of order 2, so it has two eigenvalues possible, 1 and -1. Right? And tau fixes everybody in this space, so it doesn't play any role. Okay, and these guys are themselves sub-representations of V. Right? Because tau takes them to themselves, and so does sigma. Yeah? And what are these representations? In terms of the ones I have listed here. Let's look at V1 plus. What is V1 plus? Here tau and sigma act completely trivially. Yeah? So what is that?
It's a trivial.
Not quite necessarily, because I haven't said anything about the dimension of V1 plus. For all we know, V1 plus is the entire space. And it could be a dimension of 1,000,000. Right? I started with a completely arbitrary representation of G. But what we know is that the whole group acts trivially on this space. So if I were to write it as a sum of representations, how of the ones that we have here. So the game that we're playing is we have 3 representations that we identified that are irreducible. And what I'm trying to do is find a way to use these to generate all possible representations by taking sums, direct sums. So if I look at this V1 plus, how would you write it as a sum of these? This is one-dimensional, this is one-dimensional, this is two-dimensional. So if I have a vector space of dimension 1,000,000 and the group G acts trivially, how do I write it as a sum of these? A direct sum.
Summing the trivial.
Yeah, I sum the trivial representation 1,000,000 times. Yeah, I take any basis of the space. Each vector on the basis generates a one-dimensional representation because the group acts trivially, which is isomorphic to the trivial one. Yeah. So V1 plus is a direct sum of the trivial representation, and I think I'll use the notation in Fulton and Harris. By the way, I would, if you want to have a look at a book, the first 2 chapters, I think, of Fulton and Harris will have most of the stuff we've discussed, and this is somewhat fairly standard notation, I think. So this we'll call U, this we'll call U prime, and this I think we call it V. Unfortunately, clashes with our choice. But so V1 plus is a direct sum of this U representation. U is dimension 1, so you have to take as many as the dimension of V1 plus. Whatever it is, we don't need to know. It depends on the inputs. How about V1 minus? So V1 minus is now a representation which tau acts trivially and sigma acts by -1. Yeah? But sigma is a 2-cycle, right? Which has sign minus is an odd representation. So sigma is 1, 2, it's odd. So a sine sigma equal to -1. And tau is 1, 2, 3, is even. So a sine tau equals to +1. So if we look at an arbitrary element of the group, the group is generated by sigma and tau, and the sign is is determined by the signs of sigma and tau, which are respectively -1 and 1. So what I'm trying to say is that this representation is a sum of the sign representation. Because the sign representation is precisely a one-dimensional one on where sigma and tau act like this. So V1 minus is a direct sum, or rather, I should say, isomorphic, be careful, of the sign representation as many times as the dimension. Yeah? And again, you can take any basis of V1 minus, and the lines spanned by these basis vectors will be lines in which tau acts by 1 and sigma acts by -1. And that's exactly isomorphic to the sign representation. Okay, so now that was when zeta was equal to 1 back in this argument. Now let's take zeta to be a primitive cubic root of unity. So we have this subspace, and what does sigma do to it? If we take a vector in here, sigma v lands where? Right? The argument that we did was, so what we have is the tau of v is zeta 3 of v. By definition, this is the eigenspace, well, eigenvalue zeta 3. And so if we do this, and we repeat the argument, this is this, so this is zeta 3 inverse of v, so this is zeta 3 squared of sigma of v. So that means that sigma v is in the eigenspace, but now with the other eigenvalue. So sigma goes from zeta 3 to zeta 3 squared, and sigma inverse goes backwards. So these two spaces are of the same dimension. And so what sigma does is, in our decomposition of the vector space V as a sum of eigenspaces of tau, it swaps the two eigenspaces of eigenvalues zeta 3 and zeta 3 squared. Okay, so they are not sub-representations. The sigma doesn't fix them, and doesn't fix any subspace on them. So now we can do this. So pick a basis for, let's say, v zeta 3. Let's say v1 to vr, whatever r is, the dimension, and then sigma v1 up to sigma vr is a basis for v zeta 3 squared. Yeah. And what I can do now, so let's see where we are. V was v1 plus, direct sum v1 minus, direct sum v3, v zeta 3, direct sum v zeta 3.
Why sigma is injected?
Sorry?
Why sigma is injected?
It's an invertible element. It's a linear transformation which is invertible. Yeah, all of these guys are invertible isomorphisms. Okay, so I can look at this space here and write it this is the space generated by my vectors v1 up to vr, and the vector sigma v1 up to sigma vr. And what we can do is organize this as follows. I can look at the subspaces v1 sigma v1, direct sum v2 sigma v2, dot 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 vr sigma vr. I just pair each vector with its sigma counterpart and look at the subspace, two-dimensional subspace they generate. And now what I claim is that each vi sigma vi is isomorphic to the standard representation. And the point is that tau takes, so on this basis, let me, yeah. It's not going to come out the way. Let's see, so how I'm going to do it. Yeah, it's not exactly the same matrices that we had before. For each I, we have this. I probably would need change things slightly to make them be exactly the way we had it before. So I think I don't want to try to do it here and get it wrong, so I'll leave this to you to verify. It's a simple thing, but check this. Okay, so the final thing is then that V is isomorphic to a certain number of copies of the trivial, certain number of copies of the sine, and a certain number of copies of the standard. So every representation is a direct sum of a certain number of copies of these three representations that we found. Okay, so as I was saying, we did this with the bare hands for the case of S3, but much of what we did is true for an arbitrary finite group. So what we'll see is that for any G, any finite G, there are finitely many irreducible representations and every representation is a direct sum of these. And so one of the tasks in this theory, well, first is to get to this point to prove that, but then it would be, if you have a group G, would be to try to describe these finitely many irreducible representations it has. And that's what I was telling you on Monday, that the information is contained in this atlas for the case of simple groups.
Is there any relation between the number of irreducible representation and the order of the group?
Only a loose one. What we'll prove is a little bit more than the statement, is that the number of irreducible representations is the number of conjugacy classes of the group. So S3 has 3 conjugacy classes. This is the class the class of the identity, the class of a 2-cycle, and the class of a 3-cycle. And so there's 3 conjugacy classes, and we found there's 3 irreducible representations. This will be an extension of this statement here. And it's one of those weird things in which these 2 sets, the conjugacy classes and the irreducible representation, have the same cardinality, but there is no obvious natural map between them. It's going to be, we're going to prove that they're the same cardinality without exhibiting a bijection, and in fact, in general, such a bijection can only be something artificial. As it happens for the groups Sn, there is somewhat of a natural way to do that, but it's very special to Sn. Okay, and the conjugacy classes are indexed by this types, cycle types, and they themselves are indexed by partitions of the number n, which can be described by these pictures, which you may have seen. So it consists of n boxes in rows. So this is the number of rows. The number of boxes on each row is non-increasing. So the representation theory of Sn is a very rich theory. It has a lot to do with various combinatorial things. I'm not sure how much we're going to be able to do of the general theory, but it's a very pretty story. Okay, so now in order to proceed, we have to do a bit of linear algebra. So in a certain sense, you'll see that this theory or representation of finite groups is linear algebra on steroids. And so everything that you ever seen in linear algebra will come back, and we'll do it with the group G included. And so you may have to go back and refresh some of those things in linear algebra. So for example, in linear algebra one talks about dual spaces. If you have a vector space, you have this dual. And what we want to discuss now is that if you have a representation, then you also have a dual representation. And naturally, the vector space in which the dual representation will live is the dual space, but what we want to discuss is how do you find the action. So let's say V is a representation of G, and I will stay with the assumption that V is finite dimensional, G is finite. So we have the dual vector space, which formally we define it as homomorphism from V to C. So the space of linear forms on V. And we want to define an action on this new vector space V dual that somehow makes everything natural and compatible. And so one way to do that is to look at the following. There is a natural bilinear pairing between the dual vector space and the space itself, which is just sort of follow your nose type of thing. So if you have a dual vector and a vector, then the dual vector is a function on vector, so you just evaluate it on the vector. And this is, let's call this with this bracket notation. So this is bilinear, so it's all simple to verify because everything that we're doing is linear and so on. And so we want to define, we would like to define an action on V dual, G to act on V dual in a natural way. And by this I will mean that so what we want to do is an action in such a way, so i.e. I want to give a meaning to GV dual, so that GV dual paired with GV is V dual V. So that this pairing is preserved by the action of the group. So this is going to be a bit of a formal game. So this first is the fact that if we have any map from V to V, linear, we can define a map transpose from V dual to V dual. I'll put the transpose on the left here. It goes from V dual to V dual by saying that phi transpose of a V dual, dual vector, is a new dual vector which applied to a vector V is the dual vector V applied to phi of V. Yeah? It's one of those things that if you're asked to define something like this, you just put the symbols in the only possible order that makes sense. Yeah? And so with this definition, phi transpose V dual paired with V is just a rewriting of this in terms of the pairing, has this state. So it behaves as the transpose. So if you have phi transpose on this side, you can pass it to the other side as phi and vice versa. If you pick a basis for the space V and you identify V dual using the dual basis, all of this will come out to be matrices and their transpose. Okay, but we can do it in this sort of formal way. And you can check that the transpose of the transpose is phi itself using the canonical isomorphism of the dual with V. So V and V dual are isomorphic but not canonically, but V, the dual of the dual, is isomorphic to V in a canonical way. So what we want is this, I'm going to call rho dual the dual representation we're trying to define. So applied to G, we can act it on a dual vector V dual, and on the other hand, act it on V is our rho. So we start with a rho, and I want to define rho dual. So we want rho dual such that this is the same as V dual V. Okay, so now we can use this transpose thing and move the I'm going to take phi to be rho of G. It is a linear map from V to V. And according to this discussion over here, pairing it with V dual, or with whatever, is the same as putting the dual on the other side. So what we get is that this first left-hand side is equal to putting this height over here with a transpose. But this is expected to be required to be equal to this, and V and V dual are arbitrary. So this has to hold for all V dual and all V. And so the only way that this can happen, this pairing is non-degenerate if something pairs to 0 against everybody is because it was 0 to begin with. So the only way that this can happen is this thing here has to be equal to the identity on V dual. Sorry, this row V makes no sense. This would be G. So what we get is that rho, if we want this statement to hold, it can only happen if we define rho dual as follows. So rho dual of G times rho transpose of G has to be the identity, so that means that rho transpose of G inverse and so we use, so we write it as, yeah, so I guess there's one more step to verify that rho transpose is a homomorphism, and so the inverse goes inside. So I can just use this to define the dual representation. So this is the dual representation. And we see again the inverse, as we saw when we defined a linear representation attached to a permutation one. So the thing perhaps to think about, the rule of thumb is that if you have if your group acts on a set being possibly a vector space or just a set, then the natural way it will act on functions on your set is where it acts by inverse in the argument. So somehow this inverse is associated to that, and because we have this dual space, it also requires a transpose. Now perhaps the thing to note is that if you think of concretely in terms of matrices, the map, so you know that the transpose of the product of the matrices is not a homomorphism, but rather it behaves like this. Yeah? So, and also if you take the inverse of a product, is also the product of the inverses, but in the backwards order. So now what happens if you consider both operations at the same time? Yeah, they commute, and this is the inverse transpose in the correct order. That's why I put the transpose on the left, so it doesn't get mixed up with the inverse. So, in other words, this is the natural thing you would do. You would like to consider a new representation where the G sort of acts like the G inverse in the old one. But if you do that, you won't get the action to be in the right direction, and so the transpose somehow fixes that. I mean, that's a more naive way to say what we just did.
I'm just puzzled by this part. How this row transpose come from?
Because of what we had over there, we have a map from V to V over here, and the transpose is the thing. There exists a map over here that does. So in other words, this guy I can move it over here, but then it becomes a transpose.
Okay.
So that's the definition of transpose. Yeah. So a map. So what I did was that from V to V, if you have a map from V to V, there is a natural map from V dual to V dual associated to it called the transpose, and it has the property that if phi is on the V side in the bilinear pairing, you can move it to the V dual side, but you have to put the transpose. Okay, so this is a lot of, in a sense, a lot of standard nonsense that should not completely confuse you. I mean, if you want to stick to this, that's to a large extent enough. And whatever it is that we ended up doing, the point is that given a representation rho, there is a natural thing called the dual representation. And if you think in matrix terms, the dual representation acts by combining your representation with inverse transpose. Okay? And so this is the first linear algebra construction that we're going to soup up by including how the group G acts. So as I was saying before, everything you ever seen about linear algebra, pretty much, and things you may not have seen, are going to be done again. We'll do it again here with the group G included. Okay? And it's not just because we want to, it's necessary to get this theory kind of going. So if you haven't seen it for a while, you telling me that you didn't record Jordan form and so on, so I'm not sure how much of this you might remember, but we're going to have direct sum, which I implicitly already used today, but tensor products, wedge products, homomorphisms from one space to another. All of these constructions that you do when just plain vector spaces we are going to do them again with vector spaces together with the action of the group. And so all of these constructions will, if the arguments are representations, will be again representations. So the direct sum of representations we already kind of implicitly used already. It just you act on each summand. The tensor product will also give rise to tensor products and representations. The wedge products and homomorphism between representations will also be representations. And all of these constructions will need to get the theory going. All right, so that's what we'll do on Wednesday and on Friday.